When a raw egg is placed in dilute acetic acid, the acid dissolves the shell, but the egg's membrane remains intact. When it is placed in pure water, the egg swells. In a concentrated aqueous solution of corn syrup, it shrivels.
So they're saying it shrivels. So this chapter is regarding what happens to the physical properties when we create solutions. So that's what we're going to be working on. And these are also known as colligative properties. And we'll get to that. And this is just this quick introduction. So we're talking about solutions. We have to remember a few things. It's a homogeneous mixture, meaning you really can't see that there's two or more things inside that solution. And in terms of terminology, we have two new definitions we need to think about. Well, they're not really new. We've heard of them before, which are the solvent and the solute. And the solvent tends to be the substance in the greater amount. Not always, but it tends to be. More importantly, the solvent is what causes the solute to dissolve, and the solute is the substance being dissolved. So an example of this would be like easy thing to think about is sodium chloride aqueous solution. So the solute would be sodium chloride, and the solvent would be our water. And so that's kind of an easier way of thinking about it. And then you can use that example to look at other problems and other questions that you might come across.
When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
Some other definitions and vocabulary we have to worry about in solutions are saturated versus unsaturated. In a saturated solution, what that means is you can't dissolve anymore. You're at the maximum quantity of the solute that can be dissolved. This will change with temperature, but we're not really worried about temperature at this point. We're just trying to get our definitions down. So saturated, as we can see down here, contains the maximum quantity of solute that you can dissolve. Unsaturated just means you can dissolve more. That you can dissolve more solute. You haven't reached the point at where you have maximized that quantity.
When supersaturated sodium acetate is poured onto a few grains of solid sodium acetate, the amount of sodium acetate dissolved in excess of the saturation point precipitates, forming a solid. Some of the liquid solution, which is now simply saturated, becomes trapped within the solid.
So this is an idea of supersaturation. So supersaturation occurs when you're dissolving more than you can possibly dissolve, which kind of seems counterintuitive. How can I dissolve more if it's already at the saturation point? And this is usually done by heating it up and doing some other tricks. But the example we're showing here is that since you are at the supersaturated point, or supersaturated solution above the saturation point, we could see in the demo that when this actually hits seed crystals, that's what those crystals are called in the bottom of that black plate, it instantaneously starts to precipitate, instantaneously creates that solid. And that's what gives this unstable properties, and it ends up precipitating instantly because you're above that saturation point. And so there's this other definition called supersaturated solutions, as mentioned.
We can imagine the process of mixing two liquids as occurring in 3 steps. First, the intermolecular forces of one liquid are overcome. We can then think of the liquid as being converted to a gas in an endothermic process. Next, the same thing occurs to the second liquid. Finally, these two gases condense together, releasing energy. The energetics of the overall process depend on the relative strengths of the intermolecular forces involved.
So what I want to go back to
we can imagine the process of well,
I can't pause it. What you saw at the very end is the fact that depending upon where this ends up, you can end up with an exothermic or endothermic process. So in this example, if the enthalpy of formation of the solution is negative, than that of the solvent and solute, the enthalpy of solution is negative, and therefore it would be an exothermic process. You don't have to have exothermic processes.
When a chemical hot pack is activated, the supersaturated sodium acetate it contains precipitates in a highly exothermic reaction. To reuse the cooled pack, we heat it to redissolve the sodium acetate.
And so you can have these endothermic processes where you can, it can actually be cooled. So it all depends upon where that ends up when you're looking at the different, in the energetics of it. And so you can have both versions depending upon, like in the sodium acetate, when we are dissolving it, it requires heat. That's the endothermic process. And then when it's forming that solid, when it actually precipitates out, we can see our heat is exothermic here. And so it's just showing us how we can reuse it. If we applied heat to the solid, we dissolve it back into the aqueous solution, and then when we allow it to precipitate, that's what gives us our hot pack.
What was that?
Sounded like a silo tipping over. Look, the snow's melting.
With a little help from our friend sodium chloride.
So what does that have to do with anything? Well, that's these colligative properties. And we saw how adding salt to snow decreases the melting point. And so you need to remember, when we create a solution, the vapor pressure is going to decrease, the freezing point or melting point will decrease, the boiling point will increase, osmotic pressure occurs, and the whole thing about colligative properties, which we'll talk about some more again, is this last statement here. That it really doesn't matter what the solute is. It really has to do with the solvent to solute particles. And that gives us this new type of colligative properties. And so we have 4 different types in using these colligative properties. We're going to need different units of concentration, not just molarity. And so we have 3 new units of concentration we're going to actually introduce here, and we're going to practice in a little bit. We have molarity, which is the big M. We have molality, which is the small m. We have mole fraction, which is the Greek letter chi. And then we have weight percent. And so we're going to talk about these individual units of concentration and because we're going to need them when we talk about these colligative properties.